So hello everyone. Today I'm going to talk to you about NBODY simulation for planets in star cluster. I will give you a little bit about the state of art of both planetary system and planets as free-floating planets. I will define them in a little while, and then give you three works of mine that give a little consideration how the planets in the star cluster dynamically evolve. So let's start with planetary system. You know about Kepler and how many planets have been discovered there. In this case, what I want to focus about is instead what has been found in planetary system. So there are very few planets observed in open cluster. There have been a total of 27 discovered with radial velocity and transit. And for the microlensing, we have two confirmed free-floating planets in association, many on surveys, and only one globular cluster exoplanet that was found near a white dwarf with timing variations. So why we have so few is related to the fact that only recently we managed to have observation of this planetary system, and hopefully we will have more in the future on open cluster that and we will have any more. And for globular clustering and the AMUSE cluster, neighbors light contaminate the samples, and it's very, very difficult actually to find one. Instead, for free-floating planets, we have a lot of different theories, but they are very, very few that we can find in a globular cluster or in open cluster due to the previous reasons. However, there is a lot of candidates. The only issues is that we don't know very, very little about those, and the main issues are characterized by the mass, if they are either bounded to very large orbits or if they are self-formed. If you want to see more about this, there is this GAM 2013 paper that gives a little introduction about this. And of course, we know that it can also come from bounded system. In case of free-floating planets, we have a very large estimation of 10 to 11 in our Milky Way, and we have no open cluster or globular cluster detection. Now, as I say, many free-floating planet candidates of microlenses service. As for the instrument that I use, I use basically NBODY direct simulation for all of my simulation. In this graph, you can see the number of particles with the time passing in our ears, and we pass from very few, 100 or 10 particle, up to 1,000, 10 to the fourth, and then we go also to 100,000 and 1 million that are the realm of globular clusters. In particular, we have two important works. One that managed to go over 1 million, and that is Kamla paper of 2022. And it will be mine in a little while, but related also to the presence of planetary systems. This is very huge in my particular field of planetary system in star clusters, because it will give much more information both on formation and how they dynamically evolve over time. So, for my first paper, I went and analyzed planetary system only, but in this case, a multiplanetary system that is similar to our solar system, with the exception of Mercury and Venus for computational time reasons. I use 9 different models, one with a different Virial ratio for the star cluster, with 0.5 in Virial equilibrium, less than 0.5 contracting phase, 0.5 expanding phase. And I use a different density in the sense I use the same Virial radius and different number of stars. In this case, the major thing that we have found out is that we have that the majority of planets is ejected in virialized star cluster that stay compact for a more time compared to the other ones. And we have that Jupiter completely drives the evolution over it. So the architecture of the planetary system is very important for the dynamical evolution. And here it is a summary of the star cluster that gives exactly what I told you about, but also another property of the encounter that we don't analyze here for time constraints that you find on K parameter. As for the planetary system, we also add that there is an including intradistance between planets and the mass distribution. Jupiter is very important for the evolution. It means the distribution of mass is important, and the majority of planetary system retail of planets. In a star cluster, as you can see from this table here, when we see that a little less than 90% of planets conserve all the planetary system compared to the other ones. Already, we also input an intermediate mass black hole in the center of the star cluster. This gives different information. However, for a very little introduction about NBH is that they have been only recently discovered, and of course, they are still not discovered in globular cluster cores. Because this is where we want to, of course, in my field. However, in a computational state, we know that if there is an intermediate mass black hole, if we look for the quenching of mass segregation. Very strictly, the quenching of mass segregation can be seen in this plot on the left, in which we see the evolution of the core radius. And the core radius, as you see, has a core collapse that basically go first down and then up on the core radius. And this is normally in star cluster without an intermediate mass black hole, while if we have an intermediate mass black hole, the evolution is quite steady. And it is steady the more we augment the black hole mass, like you see here. If you want to know more, we have the GIL 2008 paper about this. So we also change here the density of the star cluster, and as you see in the green columns, we have that the presence of the black hole further enhances the number of free-floating planets that are ejected from the planetary system. This is one of the most important conclusions. And we also want to highlight that we cannot discern quite clearly if the density of the star cluster or the planetary system are the ones responsible for this. The initial conditions are given that for the planetary systems, which are uniform logarithm distribution for the same major axis and circular ecoplanar orbit. So a very standard case scenario. In here, I once again show you the conclusion of what I just said, and we see that both the number of escaping free-floating planets and stars grows with the presence of the IMBH. Finally, I give you a final paper that is currently submitted to monthly notices. And in here, we use rotating star clusters and free-floating planets. So basically speaking, from this plot, I want you to take two things. The first one is that the collapse of the star cluster is a little later compared to the other ones, with very small rotational velocity as they are in this scenario. But what is important is actually the mass segregation anisotropy that you can find from Shohin 2019. Basically, the more the cosine is near 1, the more there is mass segregation anisotropy. The more the cosine of I is near 0, the more we are going to spherical symmetry. The parameter that we use here is called the angular velocity, but you can already go into the table and check that for 0.3, the laser velocity that we use, 7% of the kinetic energy is in rotational velocity, and 20% for 0.6, as you see. This is the number of ejection that is a little lower for both stellar free-floating planets in our scenario, and is particularly lower in the case of free-floating planets. But what we want to do here is to use the inclination and the azimuth to actually check how the angular momentum of those particles in the case of the star cluster are eventually ejected. It is on angular momentum. This means that as both the direction of the vector multiplication of r and v, so the position and the velocity. So we compared WV0 and WV0.6, and you can see that there is no real difference in the azimuth. This is because on Lx and Ly, so the X and Y component in which there is no started rotation, effectively there is no major changes. And in the case of both star and free-floating planets, we have a similar evolution. The case is different in what we see in the ejected particle in the case of the cosine of I, in which it is most or less distributed without rotation, and is very distributed along the I, the cosine of I in the case of stars. What the most important result here of this scenario is that free-floating planets doesn't follow this rule. Actually, they are more accurately distributed than we thought. This is a very important conclusion, because in this case we can immediately see that the free-floating planets do not follow the mass segregation in the star cluster, and therefore this basically say that only the planetary core eventually is responsible for the dynamical evolution of these objects. I give here that same conclusion that I talk about, and we give you general conclusion about all of the stuff that I just talked about here. So we have that high density star cluster are the one mostly responsible for the ejection of planetary system. The planetary architecture is very important, and for multiple planetary systems have very different scenario compared to single planetary system. The core plays a fundamental role because there are different early phases of the evolution of the star cluster. We didn't see it in detail, but as you see, as you have shown, there is this particular change, and the core structure have a very different values in the escaper. Finally, the star cluster rotation in the slow rotation regime do not enlarge the number of ejected free-floating planets, but diminish them. And this is very important because rotation is a property that is very common in realistic star cluster, especially if they orbit around a galaxy. And with this, I conclude my talk, and I'm up for questions.